In evaluating moments using either the scalar or vector approach, we can take advantage of a kind of principle of superposition. That is, we get the same value for the moment if we keep the original force vector as is, or if we break it into its components. Why would we want to do this? In the upper left-hand corner, we have a force vector whose line of action is inclined at some angle relative to the xy plane. If we are evaluating this moment using the scalar approach, it can take some effort to identify the perpendicular distance d between the point of interest of A and the line of action of F. If instead we first decompose F into its x and y components, the distances dx to fx and dy to fy are more easily identifiable. We can then evaluate the scalar components separately and add them together. Note that the specific signs shown in the upper right are specific to this example. Crossing dx in the plus j direction to fx in the plus I direction creates a vector component in the minus k direction. Crossing dy in the plus I direction into fy in the plus j direction creates a vector component in the plus k direction. If the same point was to the left of A in the second quadrant, as shown by this second point, both contributions would be negative. We have to pay attention to the signs of the individual components in this decomposition. A second important point is that the decomposed components must have lines of action that intersect the original force's line of action. From the perspective of vector decomposition, you might be tempted to put Fy over here. It's certainly a legitimate form of decomposition to form a resultant vector by adding components head to tail. But this would produce an intersection point over here, not on the original line of action of the force. When using this decomposition approach, the decomposed component should appear tail to tail or head to head to ensure that the intersection of the component lines of action lie on the original line of action of the force. In our first example, we look at finding the moment of the 25-pound force about point B. Because this is a 2D problem, we can use either the scalar approach or the vector approach. We take a look at 4 different solution possibilities. Consider first the solution in the upper left corner. In this case, we'll find the perpendicular distance d to the line of action directly. From the geometry of the problem, we'll identify several distances that will be useful in this and subsequent solutions. We have a 30-degree angle here, and if we define this distance as L, we can see that tangent of 30 degrees is equal to 8 inches over L. This gives us that L is equal to 13.86 inches. The distance d can then be found from d equals L sine 30 degrees, which is equal to 6.93 inches. The moment magnitude about B, using the scalar approach, is then F times D, 25 pounds times 6.93 inches, and that gives us a value of 173.2 inch-pounds. The sense of the moment is determined from the right-hand rule. We would cross R into F this way, and that would give us a result that points out of the plane of the screen, and that would be in the plus z direction. So it would be a counterclockwise or positive moment. The second scalar solution in the upper right corner begins by immediately decomposing force F into its scalar components. Note this is represented head to head so that the lines of action of the components intersect the original line of action. The Fy component has no moment arm and contributes no moment about b. The moment arm of Fx is just 8 inches. This gives us m is equal to Fx times 8 inches, and with Fx being equal to 25 pounds cosine 30, this once again gives us 173.2 inch-pounds. Again, the right-hand rule will give us the sense of this moment. R crossed into F is producing a counterclockwise moment that's coming out of the plane of the screen, and that's in the plus z direction or plus k direction, so it has the same sense as the moment we calculated in solution 1. The third scalar solution in the lower left corner involves sliding the force down its line of action until it crosses the x-axis at minus L, and then we decompose it into head-to-head fashion. Now the Fx component has no moment arm, and the moment is due entirely to Fy. The moment arm here is L, and the moment magnitude is Fy times L, 25 pounds sine 30 degrees times 13.86 inches, and again that's 173.2 inch-pounds. And once again we could get the sense of that moment by taking R and crossing it into F, and that's again still going to give us a counterclockwise or positive moment. Finally, solution 4 shows two different ways of evaluating the moment using the vector approach. There are two natural choices for position vectors to the line of action of F. The first is RBA that lies purely along the y-axis, and the second is RBC that lies purely along the minus x-axis. Focusing first on using RBA, we have the moment is RBA cross F, which is 8j inches, crossed into minus F cosine 30 in I, minus F sine 30 in J. We'll get no contribution from crossing J into J. We have a minus 8F cosine 30 J crossed into I, and J crossed into I is minus K, so this is going to be 8F cosine 30 in K. And once again, that's going to give us 173.2 inch-pounds. Alternatively, we could say M is equal to RBC cross F. RBC is minus L, it's minus 13.86 inches in I, crossed into that same F, minus F cosine 30 in I, minus F sine 30 in J. Only the I cross J component will survive, and we see that that gives us a 13.86 F sine 30 I cross J, which is just going to be K. And again, that's going to give us 173.2 inch-pounds in the plus K direction. Although you should strive to develop competency using both the scalar approach with the right-hand rule and the vector approach, you can always fall back on the vector approach if you can't see the sense of the moment using the right-hand rule. Example 2 shows a configuration nearly identical to problem 1 with a wrench that has an L-shaped handle. Given that the only difference in the geometry of this problem is the 3-inch horizontal leg of the wrench, it should be clear that the moment about point B is going to be lower than the result calculated in example 1 because the force's line of action passes closer to the point of interest. I will not go through 4 different solutions to this problem, but instead we'll look at one scalar approach and one vector approach. In the scalar approach, we begin by decomposing the vector f head-to-head at point A. The Fx component has the same moment arm and same positive contribution to the moment about B as it did in the previous example. Now the Fy component also has a moment arm, in this case it's 3 inches, but the sense of its contribution is opposite to that of Fx. That is, if we think about the nature of the cross product for this component, crossing r into Fy will produce a clockwise or negative value that will counter the positive contribution of Fx. The moment then, using the scalar approach, is the Fx component, which is 25 pounds cosine 30 degrees, times the moment arm of 8 inches, and then minus the y component contribution, 25 pounds sine 30 degrees, times 3 inches. And that net result is 135.7 inch-pounds. And the sign of this will be in the plus k direction. So we have the first contribution from Fx is in the counterclockwise or positive z direction in the plus k direction. The contribution from Fy is in the clockwise or negative z direction. So the net result is that this is going to be a moment that has a net value in the positive z or plus k direction. To use the vector approach, we now have this position vector to A, and we could say that M is equal to RBA cross F, which is 3I plus 8J inches. We're crossing that into minus F cosine 30 in I minus F sine 30 in J. We'll get non-zero contributions from this cross product and from this cross product, so we'll write those out as first minus 3F sine 30 I cross J and minus 8F cosine 30 J cross I. Using the fact that I cross J is plus K and J cross I is minus K, we end up with 8F cosine 30 minus 3F sine 30 in K. And once again, using F equals 25 pounds, this gives us 135.7 inch-pounds. Finally, in our last example, we have a column that is supporting a cable AB in tension. The tension pulls on the column from B towards A. This will tend to bend the column about its base at O. We are asked to find the bending moment two ways based on position vectors ROA and ROB. First, because this is a 3D problem, I would recommend the vector approach. The tension on the column is directed from B to A, so we can begin by defining a unit vector along BA so we can properly describe that tension. From the figure, RBA is equal to 9I plus 12J minus 20K meters, and the magnitude of that relative position vector turns out to be 25 meters. So the unit vector from B to A would be that position vector divided by its own magnitude. That turns out to be 9/25 I plus 12/25 J minus 4/5 K. We want to calculate the moment about O, which is either ROA cross the tension on UBA or ROB cross the tension on UBA. Using the first calculation, we have the moment about O is equal to 9I plus 12J meters crossed into 5 kilonewtons on UBA. Now, one of the things we might note here is that this position vector is parallel to this force component, so that position vector crossed into that piece of the force is going to give 0, and so the only thing we have to worry about are the contributions of 9i plus 12j crossed into the minus 4k piece, and that gives us minus 36 I cross k minus 48 j cross k kilonewton meters. Using the fact that I cross k is minus j and j cross k is plus I, this gives us 36j minus 48I kilonewton meters. We'll make a note of that result down here and then do the second operation, which is that the moment about O could also be written as ROB cross the force. So that's 20k meters crossed into 9/5 I plus 12/5 J minus 4k kilonewtons. Now the k component crossed into the other k component is 0, and we're going to be just left with the first two terms, a k cross I and a k cross j component. And we'll again have 5 goes into 24 times, so we're going to have a 36 k cross I, and then we're going to have a 48 k cross j kilonewton meters. And once again, using the fact that k cross I is equal to plus j and k cross j is equal to minus I, we're going to get this same result that we have down here, that the resultant moment looks like this. We can sketch this bending moment about O. Here's our position vector, for instance, from O to A. And we know that the moment is going to be perpendicular to both the position vector and the force vector. In this case, we're going to have a direction like this, and our moment is going to be in this direction. We'll now take a look at a couple of try-me examples from section 4.1.